Hi, and welcome to the University of New South Wales and the School of Mathematics and Statistics. My name is Thomas Britz, and I'd like to go through a solution to the problem number 86 from the course 3411. This problem is about BCH codes, and in particular we'll be looking at a two-error correcting BCH code and encoding a message, and we'll also be decoding a received message. So that's what we have to do. In order to do that, well, it involves a bit of work, both in parts A and in the part B where we have to decode stuff. But I'll go into a fair bit of detail if at some point you get a bit bored, or you can just skip or fast forward, of course. So, what code are we dealing with? We're dealing with a code over a field, and the field is given by this expression here. And then we have to both in part A where we have to encode something and in part B where we have to decode something, we have to construct the BCH code particular details for doing that, and it involves a little bit of work. But first let's look at the field. So this is the field of binary polynomials modded out by, or modulus, this polynomial here, x to the power 4 plus x plus 1. And I've written it as m of x, and here I've chosen a root of the polynomial, and I want to represent the field as powers of that root if possible. So in other words, I'm trying to find a primitive element of the field. So I look at all the powers, alpha to the power of 1, 2, 3, and so forth, and see whether they give all linear combinations of the small powers, 1 alpha, alpha squared, alpha to the power of 3, which form a basis of this field, and indeed they do. We get all the way up to alpha to the power of 15 before we get a 1, and then it would be alpha to the power of 16 before we get back to alpha. So alpha is a primitive root, and then we can represent the field either as linear combinations of a basis 1 alpha, alpha squared, alpha cubed, or as powers of alpha. So this is a useful table as we've seen in previous problems. Now, to encode a code word there, we first find a polynomial, the information polynomial, I, and the way that we do that is that we see these numbers here, zeros and ones, as coefficients of the polynomials, or this polynomial, where the very right-hand one is for the 14th coefficient, and we sort of count back in this way. So this is 13, 12, 11, 10, 9, and 8. So these are the coefficients in front of the monomials x to the power of 8, x to the power of 13, 14, and so forth. So we have x to the power of 8 from that coefficient, 0 times x to the power of 9, but then we've got 1 times x to the power of 10 and 11, and no 12, but then 13 and 14. There we go. Okay, now we've found this polynomial, and now we have to find the check polynomial, which is this polynomial modded by a polynomial m of x. We don't know what m of x is at the moment, and that we have to find that out. So m of x is going to be the product of two minimal polynomials, because we're looking at a two-error correcting BCH code. So we just have to find two minimal polynomials. Now one of them we could just choose to be this polynomial here. So there we've found one. So if we write m of x to be equal to the product of a minimal polynomial, let's call it m1, and another one, m something of x, then m1 can just be chosen to be this polynomial here. So if we write that as m of x times this other as yet unknown polynomial. Now, the reason that we write m1 there is that alpha to the power of 1 is a root of that polynomial. So in a similar way, we want to find a minimal polynomial of some other power of alpha. And how do we do that? Well, first of all, if we can find the powers of alpha that are roots of this polynomial, then we can just choose some other power. So that's in fact what we're going to do. So what are the roots of this polynomial here? Well, the alpha to the power of 1, or just alpha. And the way that we can find the rest of the roots is by looking at this number here, 2. So take that 2 and multiply it onto the powers here. So alpha squared, alpha to the power of 4, alpha to the power of 8, alpha to the power of 16, and so forth. Now alpha to the power of 16 is also equal to alpha to the power of 1. So we're going to keep cycling around if we continue to multiply by 2. So in fact these are just the roots here. And another way of saying it is that the cyclotomic set K1 is equal to 1, 2, 4, 8. That's just the exponents there. Now, we want to find a power of alpha which is not one of these, so that we can find another minimal polynomial. So we might as well just take the first one that comes to mind, not 1, 2, but let's say 3. So alpha to the power of 3. Or if you're looking at cyclotomic sets, then it would be the first number here that's not in the set. 1, 2, 3 would be the first set, so we've got K3. Or we've got the 3 here as well. So apparently we're looking at the minimal polynomial of alpha to the power of 3. Now, we could have chosen some other power, but this is just the first available one, and therefore a rather natural choice. Next, we have to find that polynomial there, the minimal polynomial of alpha to the power of 3. How do we do that? Well, we do the same thing as here. We just find the cyclotomic set, all the powers here. So we start off with 3, and multiply by 2, we get 6, 12, 24. 24 mod 15 is 9. 18, if we multiply by 2 again. 18 is the same as 3 mod 15. So now we're just back to 3, so we have these numbers here. What did that have anything to do with our roots? Well, if we look at these sets, or these numbers here, and raise alpha to the power of them, 3, 6, 9 and 12, just swapping those around, they're exactly the roots of the minimal polynomial of alpha to the power of 3. We have a theorem that says that. So if we want to find the minimal polynomial m3, then it's exactly equal to x minus the first root, which was alpha to the power of 3, x minus alpha to the power of 6, 9 and 12. And there you've got the minimal polynomial. Now, we'd like to express that in terms of just a binary polynomial without the alphas. So we have to expand. We get x to the power of 4 minus the sum of these roots, alpha to the power of 3 plus alpha to the power of 6 plus alpha to the power of 9 and 12 times x cubed, and then plus any two of these alphas multiplied together, so alpha to the power of 3 times alpha to the power of 6 and so on, and alpha to the power of 9, alpha to the power of 12, x squared minus, and then we're multiplying 3 together now, alpha to the power of 3, 6, 9 and so forth, up to alpha to the power of 6, 9 and 12. And finally, just all roots, all these 4 roots multiplied together, giving us the final term. And there we go. There's a bit of calculation involved here, but it's actually not too bad. We can use a couple of shortcuts. For instance, this last term, well, you can just multiply it out and then use the table here. That's not too hard. But you can also observe that we're talking about a binary polynomial here. So this term is going to be 0 or 1. And it can't be 0 because then this polynomial would be divisible by x, but it's irreducible. It's a minimal polynomial and therefore irreducible. So this can't be 0. In other words, it has to be 1. Okay, what about this term here? Well, alpha to the power of 3 plus 6 plus 9 plus 12. Let's have a look. Alpha to the power of 6, that's alpha to the power of 3 plus alpha to the power of 2. So these two terms, when you add them together, you just get alpha squared. Alpha to the power of 9 and alpha to the power of 12, we have them there and there. If you look at them, we've got alpha to the power of 3 both places, alpha both places, and then x squared and 1. So this is just x squared plus 1. And these terms cancel out, the binary. And in fact, all of this was just equal to 1. So that's the first term. Then these terms in the middle are a little trickier, but let's figure out what that's equal to. So we have alpha to the power of 9, alpha to the power of 12, alpha to the power of 15. In fact, we'll get that twice. And then alpha to the power of 18 and 21. Now, the two in the middle here, alpha to the power of 15, or in other words 1, they cancel out. Again, everything's binary. And we're left with 9, 12, 18, which is the same as alpha to the power of 3, and 21, which is the same as alpha to the power of 6. So these are again the numbers that we had before. They added up to 1, so that's what they will add up to here as well. So this is going reasonably quickly. Now for these numbers here, well, we've got 3 plus 6 plus 9, that's 18. The next term is going to be 3 plus 6 plus 12, so it's 21. And then we can replace the 6 by 9, that'll give us 24. And finally the 3 by 6, and that'll give us 27. If you reduce this mod 15, then lo and behold, we have a 3, a 6, a 9, and a 12. And again, you recognize that sum there. This is just 1 again, so we have minus x. And then finally we had the plus 1, and we're almost done. All we need to do now is just to see that the minus there and there, since we're dealing with binary numbers, these are just pluses. And there you go. That's the minimal polynomial of alpha to the power of 3. Okay, a little bit of work is involved here. In fact, we're not done because we have to figure out this m of x. That was equal to little m of x, or m1 of x, times this polynomial that we just found. So we have to we have to multiply this polynomial onto that polynomial to get capital M of x. So take that polynomial, multiply it onto this polynomial, and let's not do it in detail, just let's have a look at the answer, which is x to the power of 8, x to the power of 7, x to the power of 6, x to the power of 4, and 1, and we're done. So let's just write this here. X to the power of 8, x to the power of 7, x to the power of 6, x to the power of 4, and 1. Now, so, okay, why do we need all of this? Well, that was because we wanted to take this polynomial and mod it out by this m of x, which we've just found now. So, okay, you can do this in various ways. Now, if we're talking about a single error correcting code, instead of a 2 error correcting code, we'd have a shortcut. There we could just evaluate I of x in alpha, and that would give you the check polynomial there. Well, indirectly, it would give you a power of alpha, and that would give you, or some expression in alpha, and one of these linear combinations here. And that would then give you the corresponding polynomial in x just by replacing alpha by x. That little shortcut is lovely, but it doesn't help us here because we've got 2 errors. So we need to use both alpha and alpha to the power of 3. So I would just take this polynomial and reduce it by that polynomial there. Just subtract this polynomial a number of times from that polynomial until you have a polynomial that's of degree less than 8, in other words at most 7. And in fact, you'd get some polynomial like this. X plus x squared plus x to the power of 4 plus x to the power of 5 plus x to the power of 7. And there you go. Now, I didn't do that in my head. I just, you might have to do a bit of calculations. I knew the answer here. So what I really should write is, there is calculation involved. So once you've done that though, then you finally can get to an answer. C of x is equal to the sum of these two polynomials, and that'll be your Codeword polynomial. So that's, if we write it all up, we've got x plus x squared plus x to the power of 4 plus x to the power of 5 plus x to the power of 7 plus x to the power of 8. Now we're up on this polynomial, 10, 11, running out of space, 13 and 14. Just made it. This is our Codeword polynomial, and now we just need to translate it into a Codeword by looking at the coefficients. So the Codeword would then be 0 times 1 plus 1 times x, x squared, 0 for x cubed, but then there's a 4, a 5, no 6, a 7 and an 8, no 9, a 10, 11, no 12, a 13 and a 14, and we are done. This is then the Codeword, or the encoded version of this message, and you can see that it's probably right because the people setting the exam, or the person setting the exam, has made it nice and pretty, and so you recognise that and you say, oh okay, that's probably the right answer. In part B, we have to correct and decode this received message, and in order to do that, let's first look at what the BCH code is actually constructed as, or how can we represent it. And it's a generalization of the Hamming code, where we're just taking any linear combination, and in this case we're representing it by the powers of alpha, so 1, alpha, alpha squared, etc., up to alpha to the power of 14. And we're going to do the same again for alpha to the power of 3, which was what we found in part A, that we could use the third power there. So this is really sort of like two Hamming codes at once. We've got the top bit, and or the top row and the second row, and you can consider each of these rows as really 4 rows of binary entries. For instance, alpha to the power of 14 is equal to, well, alpha to the power of 3, or 1 plus alpha to the power of 3. And you can see this as a vector, or if you look at the coordinate vector for this polynomial, it's 1 times 1, 0 times alpha, 0 times alpha squared, and 1 times alpha to the power of 3. So you could replace each of these entries in the matrix there by little length 4 column vectors. And then you get a matrix of with 15 columns and 8 rows, and the dimension is in fact also equal to 8. So we have 8 check bits, and in other words we have only 7 information bits. Now 7 information bits is not a whole lot, but we are also trying to correct up to 2 errors, so that's sort of nice. So there has to be some trade-off somewhere. Okay, now how would you correct and decode this? Well, it's the same sort of thing as in the linear case, where we're looking at linear codes. We have to look at the syndrome. So the syndrome of D is just H, the error, the parity check matrix, times D transpose. And if you look at what's happening, we take that this vector here, transpose it so that it's now a column vector, multiply it onto the matrix here, so that really just singles out, or takes these numbers and multiplies them onto the powers of alpha. And one way of saying that is that this is D of alpha for some polynomial D, and here we have d of alpha cubed, and let me just draw it or write it over here. So d of alpha and d of alpha cubed. So you can express the syndrome as a little vector of length 2, where we've got some polynomial d evaluated in alpha. That polynomial d is exactly just the polynomial that we get by looking at the coefficients and adding on monomials. So we've got that d of x is just equal to nothing times 1, but we've got an x squared, x cubed, and so forth. And no powers of 5, 6, 7, but we do have of 8, and of 9, not of 10, but of 11, and then also 14. Okay, now, before we go on to trying to decode this code word here, let's have a little look at what would happen when we take the syndrome here and calculate it. There are 3 things that could happen, because we're looking at a 2-error correcting situation, so we're assuming that this message contains up to 2 errors and no more. So you could have no errors, or you could have 1 error or 2 errors. Now if you have no errors, we're talking about a syndrome being equal to 0. So you could write it like this. We have that it's the 0 vector, or 0 there and there. Let's write that maybe more specifically. If 0 errors. Now, if we have 1 or 2 errors, then we've got something not equal to 0. And that's the case for both 1 and 2 errors. So let's suppose that we have exactly 1 error and see what sort of situation we get there. So in this case, d would be equal to, if we have 1 error, we have d being equal to a code word with no error, plus some error given by adding just a binary standard unit basis vector. Here we'd have that the polynomials, d of x, well, that'd be the same as the c polynomial here, plus just the monomial x of j. So if you evaluate this in alpha, you have d of alpha is equal to c of alpha plus alpha to the power of j. Now c of alpha, that would be the syndrome of a code word c, so that's equal to 0. And you just have that that's the d of alpha is alpha to the power of j. So if you know if you calculate d of alpha and there's only 1 error, then you can see, this must be the corresponding error, or the position labelled by j is where you've got the error. In our situation, we have up to 2 errors, so we also have to look at alpha cubed, and then you have c of alpha cubed plus alpha to the power of 3 times j. Now c of alpha cubed, that too is going to be 0, because we found when we're doing the modulus in part A, for instance, we had capital M was the product of the minimal polynomial of alpha and alpha cubed. So alpha cubed is going to be a root of that modulus polynomial. So we get that c of alpha cubed is 0, and we end up with alpha to the power of 3 times j, which is just this to the power of 3, or in other words, d of alpha to the power of 3. Now the reason for talking about all of this is that if there's just one error here, then you see that d of alpha cubed, so d of alpha cubed, is in fact just equal to d of alpha cubed. So d of alpha cubed. So this is if we've got 1 error. Now, if we on the other hand don't have this situation or this situation, then so in other words, if we don't have that the syndrome is 0, 0, and we don't have that this is true either, so we've got d of alpha cubed is not equal to d of alpha cubed, then we have exactly the case in which there are two errors. So, by working out this syndrome, we can figure out whether there are 0, 1 or 2 errors in our received message, and that's exactly what we are going to do. So let's do that. So, let's see. Let's get rid of this to make a bit of space. And as in part A, there are some calculations involved, but we will get through them. We have d of alpha is just this polynomial there, evaluated in alpha. Alpha plus alpha squared plus alpha cubed plus alpha to the power of 4 plus alpha to the power of 8, 9, 11 and 14. The same is true, or the expression down here will be the same, except where we've replaced alpha by alpha to the power of 3, alpha to the power of 3, alpha to the power of 6, 9, 12, 24, 27, and 33, and finally 42. Now, again, this involves a couple of calculations that would possibly just waste time to do. It doesn't take too long though, using this table here, for instance. Alpha plus alpha squared plus alpha cubed is, if you look at the table, alpha to the power of 11. So this goes out with alpha to the power of 11. Then you, for instance, have alpha to the power of 4 is alpha plus 1. Alpha to the power of 14 is alpha cubed plus 1, so that's alpha cubed plus alpha, which is exactly equal to alpha to the power of 9. And then you're just left with alpha to the power of 8. And if you do something similar here, then you get alpha to the power of 4. So, we've found the syndrome, and if you look at it, well, it's non-zero, so there's at least one error, which you'd sort of expect because we're supposed to correct something. And we can check, are there 1 or 2 errors here? And we just see, well, this cubed, is that equal to that? So we have alpha to the power of 8 cubed, that's alpha to the power of 24, which is alpha to the power of 9, which in fact is not equal to alpha to the power of 4, so we have that d of alpha cubed is not equal to d of alpha cubed. So there are in fact 2 errors. Okay, now that helps us a lot, because then we know that our code word, this one here, can be written up as, or the received message, sorry, that can be written as a code word plus 2 errors given by EJ, for instance, and EL. And here I'm avoiding K or M because they were the numbers for the number of check bits and information bits. So if we can write D as a code word plus 2 errors, or 2 error bit vectors there, then if you look at the corresponding polynomials, then we've got D of x is equal to C of x plus x to the power of j plus x to the power of L. And if you evaluate this in alpha, you get that this is 0, so we just have that d of alpha is equal to the sum of these two. And similarly, if we had d to the power of 3, we'd have c to the power of alpha cubed, which again is 0, so we can remove it almost before we've written it down. But then we just have alpha to the power of 3j and lj, so alpha to the power of 3j plus alpha to the power of 3l. And we're sort of done. In principle, we're done. Because in order to find the positions j and l, we just have to solve this equation here. Let's have a look. You want to have that this is equal to this sum here, and this alpha to the power 4 is equal to this sum there. So you're trying to find the j and l numbers for which this would be true. And since j and l are symmetric, then there are going to be at least two answers. Well, whether you choose j to be the one error or l to be the other, it doesn't matter. So there will be exactly one pair of solutions, which corresponds to just finding the two positions out of the 15 positions where there's an error, or where there are errors. In other words, if we wanted to solve this, we could do it by trial and error. So you've got 15 positions, you're choosing two of them, so that's 15 choose 2, that's 105. 105 cases to test by trial and error. So that's a lot. But let's be sneaky and clever and reduce that number down to something far more manageable. And here's a little sneaky trick. What we're going to do is we are going to write the top bit here, the sum here, as S1, and the bottom bit as S3. Ta-da! Sneaky trick. Now, of course, that doesn't do anything except write more symbols on the board. But the reason that we did that was that now we can do the following. We can say S1 cubed, that's this cubed, alpha j plus alpha to the power of L cubed. So that's alpha to the power of, if we expand this, alpha to the power of 3 times j plus alpha to the power of 3 times L plus the other terms, 3 times this squared plus times that, and so forth. So we can express that as 3 times alpha j, alpha L, times the sum of these things again, or j plus L. And here I'll get rid of it. Now you might not be able to read this properly, so I'll just write it up again. Here in particular, this is just S3. Then we've got plus 3 times the product of these two powers, times, and this here was just S1, the sum of these. Now we're dealing with binary coefficients, so this 3 is also the same as a 1 in binary terms. And then we've got S1 cubed is equal to all of this. Why am I doing this? Well, bear with me just one more step. We've got that if we isolate the product, alpha to the power of j times alpha to the power of L, that's equal to this S1 cubed minus S3 divided by S1. So that gives you some expression, and I'll just calculate that and then tell you why I'm doing all of this. So that's alpha to the power of 4 to the power of 12 cubed minus 8 minus S3, which was alpha to the power of 4, divided by S1, which is alpha to the power of 8. So here we have that we can write this as alpha to the power of 2, or in other words 16. And here we've got divided by 8. Alpha to the power of 16 is just alpha, using this fact here. Alpha to the power of 4 divided by alpha to the power of minus 8 is alpha to the power of minus 4. Bit messy here. Minus 4 is congruent to 11 mod 15, so we could multiply alpha to the power of 15 onto this and get 11. The minus is the same as a plus when we're working binary numbers. Alpha to the power of 11 is this expression here, which if you add alpha, it gives you alpha cubed plus alpha squared. And if you look, that's equal to alpha to the power of 6. Okay, I had promised you to tell. I promised to tell you why this was all relevant. Well, if we just remove this, then we've got that the sum of these powers, alpha j plus alpha L, is equal to something, alpha to the power of 8, We also have that the product of these is equal to something. That's alpha to the power of 6, or alpha cubed plus alpha squared. In particular, we know what the sum of these is and the product of these is. So these two numbers here, these powers, are exactly the roots of a polynomial that are given by these terms here. In particular, they're the roots of the polynomial x squared minus or plus, doesn't matter here, of the sum of them, so that's alpha to the power of 8, plus the product of them, which was alpha to the power of 6, or in other words, alpha squared, alpha cubed plus alpha squared. So we're looking for the roots of these of this polynomial, and that'll exactly give us the alpha to the power of j and alpha to the power of l. Why is that an improvement? Well, up front we had to search by trial and error for the solutions to this, of which there are 105 pairs. Now we just have to find roots of this polynomial here, of which there are, well, we have to just look at these 15 here, and 2 of them will be roots. So on average you only have to search around about 7 or 8 steps, which is a vast improvement over 105, and fewer calculations too. So let's do that. So let's first test, is 1, for instance, alpha to the power of 0, is that a root of this polynomial? So 1 squared plus alpha to the power of 8 times 1 plus alpha to the power of 3 plus alpha to the power of 2. Well, that's 1 plus alpha to the power of 8, which is alpha squared, plus 1 plus alpha cubed plus alpha squared. And a couple of things cancel. Well, in fact, everything cancels except alpha to the power of 3, which unfortunately is not 0, so 1 is not a root. Okay, we move on to alpha. And you calculate, and unfortunately, this is not a root either. But we're cancelling some of these possible roots here. When you get up to alpha to the power of 9, then I think you get a root. Let's test that. So you have alpha to the power of 18 plus alpha to the power of 17 plus alpha to the power of 3 plus alpha to the power of 2. Now 18 is the same as 3 mod 15. 17 is the same as 2 mod 15. So, great. Look at this. Everything cancels out. We have 0. So one of the roots was indeed alpha to the power of 9. So alpha to the power of 9. And the other one we can find without testing anymore. We just see that the sum of these was equal to alpha to the power of 8. So alpha to the power of 8 minus one of the roots, alpha to the power of 9. And here minus and plus are the same. Well, let's look. 8 and 9. Just add these two together. In fact, you get all the powers, 1 alpha, alpha squared, alpha cubed, added together, which in fact is here. This is just equal to alpha to the power of 12. So there you go. There we've found our roots of the polynomial. They were exactly the solutions to this. So in other words, j and l are just 12 and 9. So j and l are just the numbers 9 and 12. It doesn't matter whether it's j and l or l and j, we have just found the positions there. Okay, now what did we have to do? We had to correct this and decode it. Now we've got all the information we need. We just have to figure out what positions these are in. So 14, 13, 12, this one here, 11, 10, 9, that one there. So if we correct it, this code word here, we get a 0 there, and do we get a, we get a 1 there, and we get a 0 there, sorry. Yes, and then it's then we've corrected it. Now to decode it, So this is now the corrected message. So now it's a code word. Now in order to decode it, we just have to get rid of the check bits. They were the first 8 bits, these ones here. So just get rid of them. And what you're left with is the last 7 digits, which are the information bits. And that is in fact your decoded message. So 10011101 is our answer, and we're done. Thank you very much.